Welcome back, Design Junkies, to Mechanical Engineering Made Simple. If the podcast brings you value, help support the show with a like, a follow, or leave a comment below.
Always great to be back at the workbench for another deep dive.
Oh, absolutely. And today we are getting into something that you probably walk past every single day without really thinking about it.
Right, the humming machinery.
Exactly. Like maybe it's that massive HVAC unit outside your office, or the engine block of your car, or even those heavy-duty pumps running a municipal water plant.
Yeah, and to the naked ear, it just sounds like this chaotic, continuous roar. Just noise.
Just noise, right?
Mm.
But what if you could understand the secret language that's actually hidden in those hums? Today, we're learning how to read the physical pulse of industrial equipment.
Because that hum, it really isn't random noise at all. It is actually a highly complex, incredibly precise mathematical signature.
And the whole mission of our deep dive today is to decode that signature.
Exactly. We're going to explore how that seemingly chaotic rumble can accurately predict a machine's catastrophic failure long before a single part actually breaks.
Which is just wild to think about. But before we can decode this secret language, we have to look at what a single word of that language even looks like.
Right, we have to start with the basics of the physics.
Yeah, and anyone who has taken a high school physics class probably remembers the absolute basics of vibration. Like, we know it's a periodic motion.
Yep, it repeats.
Right. And we know we measure the maximum displacement, the amplitude, in thousandths of an inch, which we call mils.
That's right, mils.
And we track the frequency of those cycles in hertz, or cycles per second. So if we just mapped a single pure vibration, it's pretty straightforward, isn't it?
Oh, totally. Mathematically, it's a perfect sine wave. You have your maximum stretch, the amplitude, and that's driven by the speed of the cycle.
The frequency.
Yeah, and you don't even need to look at the algebra to know that if you map it out on a chart, it draws a perfectly smooth, symmetrical wave over time.
It just swings out, hits a peak, swings back through the center, hits the peak on the other side, and comes back.
Exactly. The simplest form is the harmonic function. And just to put the mass to it, the displacement, x equals x sub 0 multiplied by the sine of omega t.
X equals x sub 0 multiplied by the sine of omega t. So that gives us the displacement, the max amplitude, circular frequency, and time.
You got it. But obviously, we aren't just doing math on a chalkboard here.
No, definitely not. We are physically capturing this invisible microscopic movement on massive steel equipment out in the field.
Right.
And the way we pull that physical movement into a computer is with a portable vibration analyzer. Specifically, we use an accelerometer.
Yeah, the transducer.
I was looking into the internal mechanics of these things, and they are wild. Like, we aren't just taking a microphone to a pipe here.
Oh, far from it. It's so much more sophisticated than a microphone. Inside the protective casing of that accelerometer, there's this tiny, highly precise mass.
Okay.
And it's suspended right between two pressure-sensitive piezoelectric films.
Right, piezoelectric, meaning the material literally generates an electrical charge when it gets physically squeezed or deformed.
Exactly.
It's kind of like the clicker on a gas grill, right? You push the button, apply physical pressure to a crystal inside, and it creates a spark.
That is the exact core mechanism. So, as the massive industrial machine vibrates, that tiny suspended weight inside the sensor bounces in direct response to the equipment's motion.
It's just bouncing along with the machine.
Yeah. And every single movement forces that weight to compress those piezoelectric films. A hard, violent bounce yields a hard squeeze, and that sends a strong electrical pulse.
While a soft microscopic bounce yields a weak pulse.
Right, so the transducer is literally translating physical displacement directly into real-time electrical signals.
It's converting physical motion into voltage. Which makes sense. But if we were just looking at a pure harmonic vibration, like a single clear note struck on a tuning fork, that electrical signal would draw a beautiful, clean wave.
It would, but an operating industrial machine train is absolutely not a tuning fork.
No, it's more like an entire orchestra warming up all at once. You've got rotating main shafts, meshing gear teeth, rolling ball bearings, fluid cavitation, all happening simultaneously.
Which creates an incredibly dense web of data. If you attach your accelerometer to, say, a heavy-duty turbine bearing, the raw data it spits out is plotted as amplitude over time.
The time domain.
Exactly. We call this the time domain data profile.
And looking at a time domain plot of a real machine, it looks like a jagged, messy seismograph reading during a massive earthquake. It is pure chaos.
Because it is a composite. Every single moving component in that machine is generating its own unique harmonic curve based on how fast it's moving and how much force it carries.
Right.
But in the time domain, all those individual mathematical curves stack on top of each other. They sum together to show you the absolute total displacement of the machine casing at any given millisecond.
Which is, I mean, totally fine if I just want to know if the machine is shaking itself apart. If the overall vibration is high, I know I have a problem.
Sure, it's a good overall health indicator.
But if I want to isolate the specific part that is failing, if I want to find the one broken instrument in our chaotic orchestra, that time domain is practically useless. Everyone is talking over each other.
It is extremely difficult to diagnose from a raw time wave.
It sounds to me like we are trying to unbake a cake.
Unbake a cake.
Yeah, think about it. If the time domain is the finished chocolate cake, a solid composite of all its ingredients baked together, we need a machine that magically separates it back into individual piles of flour, sugar, and eggs.
I see what you mean. And, well, we do actually have that machine.
We do.
We do, thanks to the mathematics of an 18th century French physicist named Jean Fourier.
Okay, what did he figure out?
He proved that complex, non-harmonic curves, like our messy, stacked earthquake seismograph, are really just the mathematical sum of many simple harmonic sine waves.
So Fourier's math is what unbakes the cake.
Precisely. Today, the microprocessor inside the portable vibration analyzer runs that raw data through an algorithm called a fast Fourier transform, or FFT.
FFT, got it.
It instantly processes that chaotic time domain wave and outputs a completely new perspective, the frequency domain.
Okay, so instead of plotting amplitude against time, we are now plotting amplitude against frequency.
Right.
All those stacked up vibrations get separated out. So you stop seeing a messy, jagged wave and start seeing distinct, isolated spikes at specific frequencies.
And this transformations is the holy grail for predictive maintenance. It changes everything.
I can imagine.
And the real genius is how engineers scale the x-axis on these charts. In FFT plots, the frequency axis is normalized to the machine's basic running speed.
Which is measured in revolutions per minute, or RPM.
Yeah. We look at the frequencies as multiples of that running speed.
Wait, so if a motor runs at 1800 RPM, a spike at 1800 is 1 times the running speed, 3600 is 2 times, and so on.
Exactly. And the critical advantage there is that if the machine speeds up or slows down due to operational demands, the diagnostic peak doesn't slide left or right across your chart.
Oh, because it's normalized.
Right. It stays locked in the exact same proportional location. Only the height of the spike, the amplitude changes.
That is so smart. So engineers can reliably compare historical health data across wildly different operating conditions without having to constantly recalibrate their charts.
Precisely.
Okay, so we've got our separated ingredients now. We have our discrete frequency peaks. But to actually predict a failure, we have to know what physical event is causing those peaks to appear in the first place.
Right, and that brings us to the concept of the forcing function. Every peak is driven by a forcing function. Vibration in industrial machinery does not happen by magic or chance.
It's all physics.
It is all physics. There's a distinct physical mechanical cause for every single spike on that FFT graph. A spinning shaft generates a normal peak. The meshing teeth of a gearbox generate a normal peak. Bearings generate peaks.
But those are the normal ones. What about the abnormal forcing function?
Well, things like a loose mounting bolt, a misaligned coupling, or even incipient metal fatigue that hasn't even formed a visible crack yet. Those create their own unique signatures, too.
So they leave undeniable fingerprints.
Exactly. A foundational rule of vibration analysis is that a machine's signature will constantly repeat itself until a physical event changes the operating dynamics. The mechanical pattern is literally locked into the physics of the machine.
Okay, let me test a logical assumption here.
Go for it.
Let's say I'm tracking a specific frequency pick on a massive centrifugal pump over a month. Week 1, the amplitude of the vibration is really high.
Okay.
Week 4, the amplitude suddenly drops significantly. My gut reaction is to celebrate. The vibration went down, so the machine is healing, or maybe it's running smoother or settling into its bearings, right?
Many operators make that exact assumption, and honestly, it often leads to catastrophic failure.
Wait, really? Why?
Because heavy industrial machines do not magically heal themselves. A lower amplitude simply means the forcing function has changed. It does not mean the mechanical condition has improved.
Wow. Okay, so if the machine isn't healing, what is physically making the vibration drop?
It usually points to an external variable, like maybe a variation in the fluid load being pushed through the pump, or a shift in the plant's operating temperature or ambient pressure.
Just environmental factors.
Yeah, or sometimes a component has deteriorated so severely that the internal clearances have actually opened up. This temporarily reduces the impact force right before the part completely fails.
Oh man, so it gets quieter right before it dies.
Exactly. Any variation in amplitude, whether it goes up or goes down, demands investigation.
Yeah.
You cannot assume a quieter machine is a healthier machine without proving exactly why the forcing function changed.
Okay, so if we know a drop in vibration isn't necessarily a good thing, we have to figure out what physical force actually shifted, and the forces inside a spinning turbine are vastly different from the forces inside, say, a reciprocating compressor.
Oh, entirely different worlds.
Let's look at rotating machinery first. Our notes talk extensively about rotor imbalance, and my immediate thought goes to my washing machine violently walking across the laundry room because all the heavy wet towels are stuck on one side.
Right, mechanical imbalance, uneven weight distribution is certainly a major factor. But engineers analyzing these massive machine trains have to account for a much more nuanced form of imbalance,
Which is?
the dynamic interplay between mechanical lift and gravity.
Wait, mechanical lift? Like aerodynamic lift on an airplane wing?
It involves fluid dynamics, yeah.
Yeah.
Heavy industrial rotating elements like massive steel turbine rotors are actually engineered to generate vertical lift as they spin through their bearing oil films or the gas they're compressing.
Really? They lift themselves up.
Yeah, that rotation creates pressure forces that literally lift the rotor up to properly center it within its bearing housing. The upward lift has to perfectly counteract the downward pull of gravity.
So the rotor is essentially flying inside its own bearings,
Yep.
suspended by the forces it generates.
It is flying on a microscopic film of fluid or gas. But consider the environment. Gravity and atmospheric pressure are not uniform constants across the globe. They change drastically with altitude. If you take a compressor specifically designed and balanced for a chemical plant at sea level, and you install it in a high-altitude facility up in the mountains, the physics change.
Because the air is thinner, so the lift generated might not compensate for gravity in the exact same way.
Exactly. The rotor could fall slightly off its true designed center line. Gravity pulls it down just a fraction of a millimeter more than the design intended.
And that's enough to cause a problem.
Oh, yeah. That tiny offset creates a measurable imbalance and a distinct vibration signature simply because of the altitude.
That is incredible. Just the altitude. And the environment gets even more volatile when we talk about flow instability.
Oh, for sure.
Because we are dealing with pumps, fans, and compressors moving massive volumes of gas or liquid. There's this terrifying case study about a centrifugal compressor we looked at.
The 50% load one?
Yeah. Picture this huge unit running perfectly at 100% capacity. The airflow moving through the piping and into the machine is laminar. It's smooth, streamlined, perfectly uniform.
Right. Ideal conditions.
The vibration levels on our FFT plot are incredibly low. The machine is happy. Then, a plant operator decides to drop the load down to 50% capacity.
And that's when things get ugly. When that load drops, the flow of the gas suddenly stops being laminar and becomes violently turbulent.
The air starts churning and eddying inside the housing.
Yeah, and even though there's absolutely zero mechanical degradation, no broken seals, no worn bearings, no loose bolts, that compressor can suddenly experience a 400% increase in vibration.
A 400% spike purely from angry, turbulent air smashing into the internal veins.
Massive.
If you were only looking at the time domain overall vibration, you'd probably hit the emergency stop button thinking the machine was tearing itself into pieces.
And that scenario perfectly highlights why the frequency domain is non-negotiable. If you look at the FFT plot during that turbulent flow event, that massive energy spike will isolate itself at a very specific spot.
The vein pass or blade pass frequency.
Exactly.
Yeah.
You will also see broadband white noise across the bottom of the spectrum. The mathematical signature clearly tells the engineer the metal components are perfectly fine, but the aerodynamic forces are out of control.
Wow. And we aren't just dealing with internal fluids and gases, right? Applied external forces physically warp the machine too.
They do.
Take something as simple as a V-belt drive connecting a motor to a fan. If a maintenance worker tightens that V-belt too much, they aren't just wearing out the rubber belt faster, they are physically sideloading the machine's steel shaft.
Right, they are pulling the entire shaft horizontally.
Yeah.
And when you pull a heavy shaft sideways like that,
Yeah.
you alter the internal clearances of the bearings supporting it.
You're pinching them.
You are pinching the steel ball bearings against the outer ring of the bearing, housing what we call the outer race.
So every time a ball bearing rolls past that pinched zone, it gets squeezed and creates a microscopic mechanical impact.
A rhythmic, repeating impact. On your FFT plot, you will see a massive spike at the outer race rotational frequency. The machine is literally broadcasting that its bearings are being choked.
And what about axial movement? Like if the shaft is sliding back and forth?
If the equipment has excessive axial end play, meaning the shaft is sliding along its longitudinal axis, you will see amplitudes jump at the fundamental running speed, the 1x frequency, along with the 2x and 3x harmonics.
It's just fascinating how every single movement, whether it's an over-tightened belt or angry air, leaves a completely unique fingerprint.
It really does.
And those fingerprints become downright violent when we transition from rotating machinery to reciprocating machinery.
Oh, absolutely. Reciprocating machinery introduces a completely different world of forces.
Right.
Rotating equipment is at least attempting to move continuously in a smooth circle.
Right.
But reciprocating machines like engines or piston compressors, they rely on linear movement that constantly has to reverse itself.
Pistons slamming back and forth inside a cylinder.
Yeah, the timing of those internal forces is also much more complex. Think about a 4-cycle engine versus a 2-cycle engine.
Okay.
In a 2-cycle, a piston finishes its complete journey in one 360-degree revolution of the crankshaft. But in a 4-cycle engine, the crank has to spin 720 degrees, 2 full revolutions, just to execute one complete cycle for all the pistons.
Oh, wow. So your frequency peaks aren't going to be a simple one-to-one match with the RPM of the main shaft.
They won't match, no. And the magnitude of the forces is staggering. Picture a heavy steel piston inside a reciprocating compressor. It gets driven from the bottom center of the cylinder up to the top center.
Right.
When it hits the very top, that massive piece of steel has to completely stop its momentum, violently reverse direction in a fraction of a second, and travel back to the bottom, where it stops and reverses again.
It's basically a controlled car crash happening thousands of times a minute.
It really is. The mechanical physics of that violent directional reversal create an immense, instantaneous spike of energy. It is a whiplash effect.
So you get this sharp, repeating spike in the vibration profile.
Exactly, strictly from the kinetic energy of that piston stopping and starting at top center and bottom center.
Which is totally absent in a smooth rotating machine. A turbine doesn't have that whiplash. The massive forcing function in a reciprocating machine is strictly born out of its need to violently change directions.
Which explains why their heavy cast iron frames have to be incredibly robust to handle the stress, and honestly why diagnosing them is so challenging.
Because there's so much going on.
Yeah, you are looking at an FFT plot that combines the smooth rotating frequencies of the crankshaft with the violent repeating impact frequencies of the pistons.
So if we step back and look at the whole picture, this entire field of predictive maintenance is like giving an engineer X-ray vision.
It is.
By capturing the physical displacement of a machine using a tiny suspended piezoelectric weight.
And then running that chaotic motion through Jean Fourier's mathematics to unbake it into discrete frequency peaks.
Yeah, you can isolate a pinched bearing race, a shaft being pulled sideways by a belt, or a pocket of turbulent air, all while the machine is running at full speed.
Exactly.
You don't have to shut the plant down. You don't have to open the steel casing. You are intercepting the symptoms before the disease takes over.
It is predictive maintenance in its most elegant form. You are letting the immutable laws of physics highlight exactly what is stressed before it ever reaches the point of catastrophic failure.
It's brilliant. And it leaves me with the final provocative thought for you to ponder. We've spent this entire deep dive looking at industrial machinery pumps, engines, centrifugal compressors.
Right.
But the physics of periodic motion and forcing functions do not care what the object is. If we can use an FFT algorithm to detect microscopic metal fatigue inside a steel compressor housing just by measuring its pulse, what happens when we scale this technology up?
Oh, that's an interesting thought.
Right. Think about attaching these same sensitive accelerometers to the massive steel support cables of a suspension bridge, or maybe embedding them in the concrete foundation of a skyscraper during a high windstorm or an earthquake.
Well, the fundamental math of amplitude, frequency, and harmonic motion would absolutely apply to those massive structures in the exact same way.
Does our infrastructure have a hidden vibration signature too? Could we unbake the time domain sway of an entire skyscraper to pinpoint a single microscopic stress fracture in an I-beam on the 40th floor before it ever fails? The secret language of vibration everywhere once you know how to listen.
It really makes you look at the built world differently.
Remember, design junkies master the critical few, or the trivial many will master you. If you're leaving this episode with something you didn't arrive with, drop a comment. Takes you a few seconds, but it tells me this workbench is worth keeping open.